Okay, so this is chapter 2, and chapter 2 is going to be all about chemistry. So we're going to be taking a look at, first of all, matter. And so basically, matter is defined as anything that has mass, or anything that takes up space. And so you have different forms of matter. So a solid, like ice, for instance, a gas, like steam, or a liquid, like liquid water. Another one is plasma. Typically, we don't work with plasma unless we're like in physics or higher order chemistry. But the three main ones are solid, liquid, and gas. Now, there's a couple of ways to describe matter. One is as elements, and an element, which is basically what you see on a periodic table, is kind of the building blocks of matter. So it's essentially the building materials that you need to develop any kind of matter that you want. And so typically we define an element as a substance that cannot be broken down into any other substance. Okay, so it basically is a pure substance. Okay, that's kind of the idea that we think about this. Substance. And so the universe is made up of all these different elements that we see in there. However, in the human body and in living organisms, the overwhelming majority of the atoms that are in our body are made up of either carbon, nitrogen, oxygen, or hydrogen, so CHON. It actually forms sort of on the order of about 96% of our overall atoms in our body. So here's kind of our periodic table that we have here. An order of all the elements that we see in nature, organized by what's called atomic number. Okay, so the atomic number is basically the number of protons. So when you take a look at another way, an alternative way of actually describing matter, we come to the idea of the atom. And so the atom we define as the smallest unit or the basic unit of matter. Now, what does this mean? What this basically means is this is the smallest that we can get. And still retain the properties of the element. So for instance, the example I always like to use in class is of the element gold, right? So gold, which isn't on this little abbreviated periodic table, is AU. And so gold has a lot of different properties, right? It has luster, it has kind of a yellow color, it's soft or malleable, it's conductive. All of these are physical attributes are encoded in the atom. And so the smallest that we can get and still be identified as gold itself is going to be at the atomic level. Now, it's atoms that come together to form molecules. We talked about in the last chapter, right? So for instance, the example I used was the example of hydrogen coming together to form water with oxygen, right? So here's one hydrogen and an oxygen. These guys form together to create basically water, and that's your molecule. And so you have two hydrogen atoms and one oxygen atom. Now, within an atom, because this is the fundamental product or the fundamental part of the material that we're made out of, we have three major pieces or subatomic particles of the atom itself. Now, the first two, 1, 2, and 3. So the first two basically are going to be in the nucleus. And the third one is going to be in what's called the electron cloud. So in the nucleus, we have a couple of major particles. So first of all, we have neutrons, which are neutral in charge. They tend to be large in mass, and they're typically abbreviated as N0. And then also in the nucleus, you have protons, which are positively charged, also large, about the same mass as a neutron, and they tend to be abbreviated P+. So in a nucleus, for instance, you'll have these protons in the nucleus itself. I'm going to draw 3 protons here, positive charge, and 3 neutrons, no charge in those guys, and that's in your nucleus. And then whizzing around the nucleus are going to be electrons. Now, electrons are negatively charged. they orbit around the nucleus in what's called electron shells. And so these tend to be vanishingly small size-wise, mass-wise, very tiny. It's almost as if they're in danger of winking out of existence. They're so tiny, and they're abbreviated E negative. And so basically what you have are electrons that are whizzing around in this cloud-like structure, the atom, like this, in what is essentially the electron cloud. And so this is kind of what it looks like. Here's a schematic diagram of an atom, a couple of different atoms. So the simplest one that we have is of the hydrogen atom, which has one proton, that's the atomic number, and one electron. So here's the electron right here. And so that's the simplest one, right? So one proton, one electron, and that is the simplest version. Now carbon, which has 6 protons and has 6 electrons and 6 neutrons, has 6 of everything. So it's going to have a ring-like structure that looks something like this. So you can see you have 2 on the inner electron shell, and then you have 4 on the outer electron shell. Now, the important thing to remember is this little kind of diagrammatic look is what's referred to as the Bohr model. It's kind of a galactic model where the nucleus is the center of the universe, and you have electrons that are orbiting the nucleus. But in this particular case, each shell, which is one line or one little ring, has a particular energy signature to it. For instance, this guy right here, which I refer to as n equals 1, has the lowest level of energy. And it has a max capacity to carry 2 electrons. From there on out, each shell, like for instance, this guy right here, n equals 2, has a max of 8 electrons that it can carry. So for instance, with carbon, what that basically means is that you only have 4 carbons in that n equals, then you have 4 different holes or seats, if you will, that are empty that you can fill in with electrons. Nitrogen, which has 7 protons and 7 electrons, will have 5 electrons in its outermost shell. So it has basically room for 2 seats. And oxygen has 6. So basically it has 2 electrons in the inner shell and 1, 2, 3, 4, 5, 6. So it has basically room for, nitrogen has room for 3 more, and oxygen has room for 2 more. So if you're taking a look at how many it takes to fill out this outer shell, which has a maximum of 8, carbon needs 4 more to fill the shell, nitrogen needs 3 more to fill the shell, and oxygen only needs 2 more to fill the shell. Now, the important thing to remember is that when you take a look at the information of these atoms, the most important one that you see is the atomic number. The atomic number is basically the number of protons. And so this basically is like your atomic ID. And here's a good example. Let's use these guys right here as our example. So here you can see atomic number is the topmost number just above the elemental symbol. So for instance, if you were to have carbon, which has 6 protons, that's its atomic ID. So it identifies you as carbon. Now what happens if I add 1 more proton? I have 7, but that means I'm no longer carbon. I'm now nitrogen. Or if I take a proton away, I then become boron. So your number of protons is your atomic ID. So if you take away a proton or you add a proton, you're changing your identity. And so this is your atomic number. Now, in addition to this, you also have what's called your mass number. Now, your mass number is going to be underneath the elemental symbol. So for instance, here you can see for lithium, your mass number is 6.941. Your atomic number is 3. That's the number of protons you have in the lithium. Now, your mass number is going to be given by the number of protons plus the number of neutrons. Why not electrons? Because electrons are too small to add to the mass. It's kind of like weighing a dirty watermelon. You don't account for the dust in the watermelon because it's negligible. So both protons and neutrons have the same mass, basically defined as one atomic mass unit. So they're large, and this is a large quantity. Electrons have very little mass, so not really much mass at all. So the mass number is essentially the number of protons plus neutrons. Now, the atomic mass, that is to say, what we see on the periodic table, is actually the average of all the isotopes of that atom that occur in nature. So let's take a look at the idea of isotopes. So an isotopes is basically a situation where you have atoms of the same element. That means they say they have the same atomic number, the same number of protons, but they have a different number of neutrons. And so because of that, they differ in their atomic mass. Here's a good example. So with carbon, I have three different types of isotopes. I have carbon that is 12. I have carbon that has a mass of 13. I have carbon that has a mass of 14. In all cases, carbon has 6 protons, which is where I'm putting this information. So this lower case 6 is the number of protons, the uppercase is the mass. So in the case of neutrons, in this case, carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. So these are all isotopes of each other. Why? Because they're the same. And what makes them the same? The protons. What's different about them is the number of neutrons. That makes them isotopes of each other. And so when you take a look at the atomic mass that you see on the periodic table, it's basically an average of all the relative abundances of all these different isotopes. This is one of the reasons why carbon is not exactly 12. It's 12.01. That's because the carbon 13 and carbon 14 makes that number a little bit heavier than 12. It's kind of putting your thumb on the scale. Now, this is also helpful because we also have in nature radioisotopes. These are unstable isotopes that are basically large. Typically, if they get too large, they get unstable. And then they emit an energy called radiation. Now, radiation, which is pure energy, is problematic because it can damage cells, it can mutate your DNA and cause cancer. However, we can use it in order for our benefit, right? So for instance, we can use radiation to kill bacteria, to sterilize things. We can also use it to kill cancer cells because it's toxic to cells. We can also use it to highlight parts of the body. So here's a good example of the radio imaging. In this case, we use radioactive iodine. And so the radioactive iodine will go to the thyroid, and then it allows us to basically highlight the thyroid so we can see it. We can also use a radioactive tracer to highlight different areas of the brain as well. So we can use this for imaging. Now let's take a look at molecules versus compounds. So molecules versus compounds, essentially molecules are atoms that are bonded together. For instance, I used the example before in chapter 1 of H2O. Also, 2 atoms of oxygen that are bound together is also a molecule. They can be either same or different. For instance, oxygen is the same and water is different. Now, typically compounds are only made of different atoms. So for instance, oxygen would not be a compound, but it is a molecule. And water is a compound. So basically, a compound is defined as something that can be separated into 2 other substances. So water, for instance, can be separated into hydrogen and oxygen. Now, generally speaking, holding these atoms together are 2 different types of chemical bonds. You either have ionic bonds, which is essentially what we think of when we think of salts, and we have covalent bonds, which are non-salts. So if we take a look at ionic bonding, one of the important things to remember about chemistry is that atoms are happy. when their valence shell, that is to say that outer shell, is full. This is one of the reasons why we wanted to take a look at those outer rings as how far do they have to go to be full, right? So for instance, this is your valence shell. So in carbon, your valence shell, which is the outermost shell, has 4 electrons in it. That means carbon's valence is 4, has 4 valence electrons. We can abbreviate that. So for instance, we can either draw carbon like this. So there's our nucleus. Here's our first shell. The first 2 of 6 electrons goes in the inner shell. The second ring is going to have 1, 2, 3, 4, but you have 4 more to go. So typically we can abbreviate this in what's called the electron dot diagram. To just show us our valence electrons. So 1, 2, 3, 4, that's what carbon has. And so that's kind of an easy way for us to basically take a look at that and to recognize that, because ultimately what happens is in this, it's the valence electrons that drive bonding. This is what drives 2 atoms to form a relationship with each other. And in the case of the ionic one, atoms will either donate or they'll take electrons to fill their valence shell. So it's a transfer of electrons. And what this does then is it creates ions. So you either have a positive ion or a negative ion. For instance, sodium chloride, which is table salt. This will form either the sodium ion, which is a +1 ion. Why? Because it picks up or loses an electron. The chloride ion, which picks up an electron. So that's going to be negative. So the ionic bond is the attraction between this positive and negative charge. So here's kind of what salt looks like. So here's your sodium. Sodium, if you kind of go back to your periodic table, which is Na, has 11 electrons here. And so when you take a look at sodium, it's going to have 2 on the innermost ring, right? So that's going to be the lowest energy one. That has a max of 2, right? That's where you can go. Everything from then on out, whether it's ring number 2 or 3, 4, 5, 6, 7, all has a max of 8. So here you have a max of 8 here. You fill that up with 8 of them, but you still have 1 more left, right? Because 8, 9, 10, you still have the 11th one. You open up a new ring, which is N3, you have a max of 8 again. You put your next electron in there. Same thing is true. So if you were to draw the electron dot diagram for sodium, it would just have 1 dot. Chlorine is the same thing, only in this case you have 17 electrons. So you have 2 on the inner, you have 8 on the outer, and 7 on the outermost. So an N3 equals 7 electrons. So you're 1 shy. So you got 1 hole left. So for chlorine, the electron dot diagram would be 1, 2, 3, 4, 5, 6, and then 7. And so you'd have 1 more left. So what happens in the ionic is the sodium will donate or give the electron to chlorine, allowing chlorine to pick up an extra negative electron, making it a negative chloride ion. The loss of that electron will allow sodium to have a slight positive charge. You have more protons than electrons, and that creates your positive ion. And so this is kind of what a salt crystal looks like. So you basically have these positive and negative ions stacked, alternating. So plus to negative, negative to plus. So the pluses are surrounded by negatives. And the negatives are surrounded by positives. So they're kind of stacked like that. And then that basically forms a little square-like salt crystal. Now, covalent bondings are essentially when you have to share electrons to fill their shells. And so ultimately, each atom is a partner in this shared response, right? So each is a partner. And so you can either share them equally or share them unequally. And so as a result, you can also form multiple covalent bonds. You can either have a single bond like this. So that little line represents a bond, a pair of shared electrons, or you can do a double bond like this. That represents two bonds or two pairs of shared electrons, or you can do a triple bond like that. And that's three pairs of shared electrons. So here's kind of what they look like. So here is an oxygen with a hydrogen. So here you can see oxygen has 8 overall electrons, 2 on the inner, and then 6 on the outer. But it's got 2 spots left over. But guess who has 1? Hydrogen has 1, and so hydrogen can donate or share an electron. Actually, could do that twice with oxygen. And so here you can see the bond where you share the electrons between oxygen and hydrogen, creating water. So that's, if you do an oxygen, you can do double bonds. So here are 2 oxygens. You can see each oxygen has a hole to fill. So they can share 1 between each other. So that's going to form 1 shared pair. That's going to be 1 bond. And then this one here, they can share these guys right here. That's going to be the next bond. So this is going to be another bond. So this is a double bond between 2 oxygens because they can share with each other. So now let's take a look at water and life. So basically, when we're going to be taking a look at water, we're going to be focusing on water as the most abundant molecule, the most important thing that we have. We are essentially mostly made out of water, between 2/3 and 3/4 water. The important thing about water is a polar molecule. That basically means that there is an attractiveness toward the electrons for some of these atoms. For instance, oxygen kind of attracts electrons toward it. So what that means is, in an oxygen-hydrogen bond, the electrons are going to want to go and spend more time around oxygen. Now what that means is oxygen looks relatively negative and hydrogen looks relatively positive. That creates polarity. You have a positive pole and a negative pole. And we take a look at water in general, you can see that you've got your 2 bonds right here. But because the electrons tend to get sucked more toward oxygen, it creates a negative pole around the oxygen, and the hydrogens tend to be positive in nature. So water is a positive molecule. So this basically sets us up for what's called hydrogen bonding, which is an attraction between positive hydrogens and negative oxygens. It's an electrostatic attraction. Between your polar charges. Very similar to static charge. So if you take a look at a water, so here's one water, has a slightly positive on these hydrogens, negative on the oxygens, then typically what can happen is this negative can be attracted and zipper up to the positive charge of another water molecule. And this would be the hydrogen bond. Now, it's a relatively weak bond, but in numbers, it can be strong. For instance, a gecko walks up the glass wall of a terrarium by using hydrogen bonds on its feet. But because it's got thousands, millions, millions of hydrogen bonds on its feet, it's able to hold its body weight up. So that's kind of what it looks like. This is water. So you can see how each water molecule is attracted to each other, and they kind of create this sort of lattice work of hydrogen bonds, all interconnecting these water molecules. Now, this hydrogen bonding of water is what gives us ultimately the properties of water. And so what are the properties of water? Well, first of all, the one huge property that we have of water, some energetic properties, is that water has a high heat capacity. Basically, this is the ability of a substance to absorb heat without changing temperature. So essentially, you're looking at the idea of a calorie, which is a unit of heat. And a calorie is basically, and just like heat capacity, is the ability to raise 1 gram of substance, or water in this case, 1 degree Celsius. So what this does is it creates, it kind of buffers against temperature changes. So if you're ever wondering, the high heat capacity of water is the reason why coasts on ocean coastlines are cooler and more temperate than, say, inland. The perfect example of this is California, where the California coast is cool and temperate. Like in San Francisco, the average high in San Francisco is like in the 60s, plus or minus a few degrees, pretty much all year round. But as soon as you go into Sacramento in the Central Valley, what you end up getting is much, much hotter temperatures. Could be up in the hundreds during the summer. Temperature it's unheard of in the San Francisco Bay Area. Why? Because of the absorbing capacity of the ocean. So the ocean absorbs that heat and keeps those air temperatures down, so it's not so hot. So that creates a lot of habitat for organisms to live in. Water is also has a high heat of vaporization. So this is basically the temperature at which a liquid turns to gas. So ultimately, in order to vaporize, you have to break those hydrogen bonds, which they tend to reform, and then it'll basically evaporate. So you have to put a bunch of energy into these hydrogen bonds in order to get them to evaporate. What this basically means is that we don't evaporate under high temperatures because we're mostly made out of water. So it's kind of what it looks like. So how water looks like under different temperatures. So basically, we have a solid that's ice. This is essentially when freezing is occurring. And then we kind of have a little bit of ramp up, and then we have the liquid phase of water, and then we have a little bit of a ramp up into the gas phase. And that's the point of vaporization, right about here, boiling point. So that's the point you'd have to get to in order to get to the high heat of vaporization. So the fact that our heat of vaporization is high basically means we can go outside on a hot day and not just turn into a steam cloud. And that's good for us. So water's properties as a solvent. So when you take a look at water as a solvent, this basically means that it can dissolve a lot of different stuff, many substances, polar mostly, and uncharged or charged molecules, which is a lot, like ions, for instance. Typically, in any given solution, you have 2 different parts, right? So every solution will have, first of all, the solvent, which is what does the dissolving. And then you have the solute, which is what gets dissolved. And so anything that's dissolved in a solvent is what's referred to as aqueous. So basically, if water is the solvent, we refer to it as aqueous or dissolved in water. So for instance, salts, because they're ionic, they're charged, will dissociate and separate. We also have polar things that are like water that have positive and negative tails on them. Those will also dissolve in water as well. So when you take a look then at the solvent properties of water, it's only going to be going after other polar molecules. That is to say, polar molecules are molecules that are very similar to water. They attract water. They're what's referred to as hydrophilic. So hydro basically means water, loving. So these are all basically polar molecules and charged molecules, just like water. If you're not like water, then you're what's referred to as hydro-water phobic, fearing. These are non-polar molecules. That means they don't have a positive and negative pole on them, and they're uncharged. And these guys won't dissolve in water. An example is oil, right? So basically in these non-polar molecules, they don't dissolve in water. And there's a mantra in chemistry when you talk about things that dissolve in other things, is they say like dissolves like. So water, being polar, dissolves other polar things and charged things, or in this case, other hydrophilics. Non-polars will only dissolve other non-polars. So like only dissolves like. Now, when you're taking a look at covalent bonds, you have non-polar covalent bonds, which are really important. And these guys are essentially two atoms that basically share electrons equally. So it's like an equal tug of war. For instance, an example of that would be atoms with the same strength of their attraction toward electrons. And so these guys are referred to as nonpolar because they have equal pull on the electrons. It's a stalemate. Now, that's a nonpolar. A polar covalent is essentially where two atoms share electrons unequally. So one's stronger than the other. So in this case, you have, say, for instance, oxygen and hydrogen, right? Oxygen has a much stronger attraction to the electrons, so it tends to pull those electrons toward it. So you see this electron cloud with all these electrons hanging out by oxygen. And then hydrogen is relatively positive because it lost all the electrons. So this is what creates polarity. So that's a polar covalent. So they share them unequally. Now, continuing on with the properties of water, another important property of water that we have is cohesion. This is basically where the water molecules will cling to each other through hydrogen bonds. And this kind of allows water to sort of stick to itself as it's flowing. Adhesion is basically where they cling to hard surfaces like blood vessels and things like that. Also, when a raindrop sticks and smears on a glass windshield. So an example is the raindrop coming down is basically oblong because the force of gravity is pulling on it, but all those water molecules are hooked or connected to each other through cohesion. As soon as it hits a windshield, glass windshield, then it feels adhesion. Those water molecules stick to the glass and it spreads out on the glass. So that's basically where adhesion comes into play. The other one is also the density of the solid. So the solid is actually less dense, which is crazy talk, than the liquid. And so that's because it expands as it freezes. And we'll see this here in just a second. And it allows ice to float on liquid water. If that wasn't the case, what would happen is if you had a lake, that top layer would freeze over, creating your little ice shelf. But if ice was more dense than water, what happened is it would sink to the bottom, and then the next layer would freeze and then sink, and then freeze and sink, and eventually what you would end up getting is a solid frozen through lake, and that wouldn't be amenable to life. Okay, so the fact that you actually have a living aquatic ecosystem underneath ice shelves is a testament because of the density issues of water. So it's kind of what water looks like. So here's your drop, so you can see how the water molecules are all kind of packed together, connected with hydrogen bonds. And then once it freezes, it basically forms this kind of expanded structure, this network. This is the reason why ice expands. So if you've ever put water in a water bottle, put it in the freezer, it blows out of the water bottle. That's because the ice is expanding. When it expands, it makes it less dense because it's fewer molecules per unit space. And that's the only thing that we know of that does that. Everything else, the solid is more dense than the liquid. Now, we also have the idea of acids and bases. So water basically forms the backbone of how we understand acids and bases, because ultimately acids will dissociate in water, releasing hydrogen ions. And this basically is what creates acidity. For instance, hydrochloric acid will dissociate in water to create hydrogen ion and the chloride ion. So this is basically what creates acidity. And I apologize, this, you can expect that usually every single session, PowerPoint will collapse on me. So so this is basically creates acidity. So basically, the more hydrogen ion you have, the greater your acidity, including the nature of the burn and the sour taste. Okay, so that's a shorthand to say concentration of whatever I put inside. When you take a look at bases typically will either take up hydrogen ion or they'll release hydroxide ion. For instance, sodium hydroxide is a strong base. So what happens here is these two guys fall apart into your sodium ion and your hydroxide ion, which basically creates a strong base. Now, in order to measure acidity, we come up with a 14-point scale, which is called the pH scale. And so it's a measure of acidity and basicity. So it ranges from 0 to 14. So 7 is neutral. And this is basically where the hydrogen ion concentration is equal to the hydroxide ion concentration. That's where 7 is. If it's below 7, it's acidic. This is basically where your hydrogen ion concentration is greater than your hydroxide ion concentration. That's from like 0 to 6.9. And then if it's larger than that, it's a base. And so this is basically where your hydrogen ion concentration is less than your hydroxide ion concentration, which is typically 7.1 to 14. And these all change by a factor of 10. Why? Because it's a logarithmic scale, similar to the Richter scale for earthquakes. So this is kind of what pH looks like. So here you can see your ion concentration as it's getting smaller. So this is the small side. So this is little, this is large amounts of ion. So the more hydrogen ion you have, the stronger your acid. So your pH is actually going to be lower when it has high ion concentration. So hydrochloric acid, for instance, is down there. As you kind of move up, you got stomach acid and lemon juice coming in around 2. Vinegar, soft drinks, beer, that's coming in around 3. Tomatoes are coming around 4. Black coffee is coming around 5. Urine is coming around 6. It's a little bit on the acidic side. Pure water is around 7. Seawater is at 8. Baking soda is coming around 9. Salt Lake, right? They don't call it the alkali phthalates for no reason. That's coming around 10. Household ammonia is around 11. Bleach is coming around 12, 13. Sodium hydroxide, that nasty stuff we just saw, is coming around 14. So notice, basically what we see here is things we eat. So we have a lot of acid tolerance, but not so much base tolerance. Now, that leads us to the idea of buffers. A buffer is basically a solution that resists pH change. So if you add an acid, it keeps the pH the same. If you add a base, it keeps the pH the same. This is important for the body because enzymes only function within narrow pH ranges. So basically, and so within us, we have a buffer system. It's a carbonic acid bicarbonate buffer system. It's in our blood. And this is basically how we regulate our blood pH. So basically, it kind of looks something like this. Take some CO2 and some water. And that's going to turn that into carbonic acid, which is what that is right there. That will dissociate, like any good acid, into hydrogen ion that creates our acidity, plus our sodium bicarb, which is basic. These are reversible, so we can basically regulate our pH using that. So let's go ahead and take a look at some of the molecules of life. So now basically we're going to be looking at organic molecules. We have four major types of organic molecules. First of all, we have carbohydrates, lipids, proteins, and nucleic acids. And these are basically the molecules of life. They each are composed of subunits called monomers, which will build the large molecule called polymers. And so ultimately we have two processes that are at play. So dehydration reaction is a synthesis reaction that removes water, hence the term dehydration. And it links the subunits together. So basically you have monomer, that means one thing, which will link these subunits together into macromolecules called polymers. And it's going to use dehydration reaction to do that. Now, to break down the polymers into monomers, you use hydrolysis. And so that's the addition of water, and that breaks the molecules into their subunits. That's kind of what it looks like. So here, one subunit. Here's another subunit. Notice you've got pieces to it. So you've got a hydrogen there, you got an OH there. So what's going to happen is it's going to take this hydrogen OH and it's going to basically put that together in water, and it's going to connect these two subunits together, and that creates your polymer. That's dehydration synthesis. To break it apart, you're going to go the opposite direction. You use water to break that bond up, and then you're going to add the OH and the hydrogen onto each subunit, and that's going to basically create your monomers. So here's your monomer coming from your polymer. So that's if you're going this direction. So for carbohydrates, basically, we're going to be taking a look at carbohydrates and each one of these guys in turn. And so carbohydrate is a huge energy source. So in plants, they can be structural as well. Typically, they're made up of carbon, hydrogen, and oxygen in a 2-to-1 ratio. And so when we take a look at the building blocks, so these are what's called the monosaccharides. These are the building blocks. And they're made of a single sugar subunit. They form the carbon backbone. And typically they'll either have multiple different carbons. So for instance, a pentose will have 5 carbons. Another thing is if the suffix OSE basically means it's a carbohydrate. So for instance, glucose is the most common one, and it's used as our ultimate energy source. If we take a look at glucose, what it looks like, it's C6H12O6. Notice it's the 1 to 2-to-1 ratio. So you have 6 carbons in this one, making it a hexose. And you can see just different ways of writing glucose. So you can see that basically you have a ring structure with these OH groups either above or below the ring. Now, when you start hooking glucoses together, you're going to start forming disaccharides. So this is basically a combination of 2 saccharides. So sucrose, for instance, table sugar, is a combination of fructose plus glucose. Lactose is a combination of glucose plus galactose. And so ultimately, these are the different disaccharides we have. So for instance, when you take a look at your 2 glucoses, you can see you have your OH here and your hydrogen here. That's going to be the components of water that's going to leave. And then those pieces leave. And then what's going to happen is you're going to take this carbon and connect it to this oxygen right there. So that's this guy right here. So this is a glucose and a glucose, which is the disaccharide maltose. And so you just basically created a maltose, a disaccharide, using that dehydration synthesis. Now, if you continue this, you start creating what's called complex carbohydrates. These are long polysaccharides, polymers of glucose subunits of varying lengths. You can do whatever length you want. Typically speaking, this will form starch, which is basically energy storage in plants. So it's nutritional for a plant. And in animals, we store it as glycogen, which is energy storage in animals. We store it in our liver and our skeletal muscles. Now, the structural stuff, this is the energetic stuff. The structural stuff is basically cellulose in plants, plant cell walls. And so like when you're eating a plant, the cell wall structure is basically cellulose. And so this is undigestible. See, these are indigestible types of carbohydrates. And we refer to this as fiber. So cellulose, basically, a good example of cellulose is essentially those fibrous strings associated with celery. So it's kind of what cellulose looks like. Excuse me, what starch looks like. So here you can see your long chain of glucoses linked together. And then it kind of forms this like little kind of twisted sort of ring here. So this is basically it. And then, of course, you can start to form branches coming off of each side of it here to pack more in there. So this is kind of what we'd see like a potato. These are the kind of starches that we see in potatoes. This is digestible. That's a plant starch. Glycogen, that's what this one is here. You can see similar concept. So you basically have these corkscrew-like structures, but you have a lot more branches. So to the point where you can't even tell where the branches are. And this is because we need to store glycogen in small spaces in our liver granules, in our liver cells, and in our skeletal muscles. So we don't have like a special structure like a potato to put this into. And then we have our cellulose. We can see it kind of forms, instead of that kind of corkscrew-like structure, it forms long linear sheets, and you can pack that down into these long fibrous ropes of cellulose. So really tight fibrous ropes of cellulose that can be woven together. And that's what creates the cell wall. So then lipids, the next one. So basically, when we take a look at lipids, we're going to be looking at fats, phospholipids, and steroids. And so ultimately, we're going to be looking at how each one of them works in us. So first of all, lipids, do not dissolve in water. That means they're nonpolar. And that also means they are hydrophobic in nature, like oil, okay? So they don't have any hydrophilic groups. There's a lot of different types in them. So you have triglycerides, which are fats and oils, phospholipids, which are important, steroids, which are important. We'll take a look at each one of these here in just a second. So a triglyceride is basically structurally made up of what's called a glycerol backbone. So it's a 3-carbon backbone. It's actually a type of sugar, that 3-carbon backbone, and to it is attached 3 fatty acids. So you have a fatty acid chain, which is just basically a long chain of carbons and hydrogens. So if you take a look at a fatty acid, basically what you've got is this sort of long chain of carbons like this. It's all full of hydrogens. And then it has attached to it an acid head group. So that's a fatty acid. That's what these guys, these little chains look like. So the tri is because of the 3-carbon backbone and the 3 fatty acids associated with it. So the fats typically are usually coming from animal origin. So things like lard and shortening, bacon grease, for instance. And they tend to be solid at room temperature. And the oils tend to be plant origin, right? So like olive oil, for instance. And they tend to be a liquid at room temperature. So if you take a look at them, so here's your glycerol backbone. So here's your 3 fatty acids you're going to attach to them. And then once you attach it, you create your fat molecule. So your triglyceride is actually your fat molecule that we measure, like in your blood chemistry. So triglycerides are hydrophobic, and so they will clump up in your body fluids. So what happens is you have emulsifiers and proteins whose job it is to carry these things around. And so ultimately you emulsify them. Basically, they make them an emulsifier. Emulsifier emulsifies them or disperses them in water. So for instance, if you have an emulsifier, so here's a little fat droplet. An emulsifier will actually stick, you have a hydrophobic tail, and what will happen is it'll stick its little tail into the droplet. So it has a hydrophilic head and a hydrophobic tail. So basically what it does, it allows this to be able to move around in water because of these hydrophilic heads. So it emulsifies it. And we see that oftentimes with salad dressing. So if you've ever seen a vinaigrette where the oil layer isn't just like all sitting on top, it's just kind of all broken up into little bubbles, that's an emulsifier and it's breaking up that oil into smaller and smaller pieces. Waxes, on the other hand, basically are typically fatty acids that are attached to an alcohol group, which is an OH group on it. And so this will oftentimes prevent moisture loss, so they're thick. As cerumen, for instance, earwax is an example of waxes in our body. So the fatty acids, like I mentioned before, are long chains of carbons with a COH. This is that carbon, that's that acid group. So this is an acid group. And so it can be either what's called saturated or unsaturated. Basically, this basically says there's no carbon double bonds in it. And unsaturated means there's multiple carbon double bonds in it. So when you take a look at a saturated fat, you have no double bonds like what I drew before. So essentially what happens is you have all these single bonds. That's a saturated fat. Now what happens is these fats, when you kind of form them, will form relatively straight tails. So their straight tails will pack together very, very strongly. And so that basically means that you're getting very strong solid room temperature. So it's dense. So the density of fatty acids causes thick packing. And that creates a solid at room temperature, like lard or bacon grease. Unsaturated fats is basically where they have one or more double bonds. So basically they have a carbon, and then all of a sudden you have a double bond in there, or a few double bonds in there. And so every time you have a double bond, it forms a bend in your fatty acid tail. So instead of being a straight chain, it actually forms a kink. And so when you have a kink in your tail, it causes problems. You can't actually put as many in there because those tails are getting in the way. So you have less dense. So you have less packing. And more fluidity in the tails. So they basically don't bend as much. So this is kind of what it looks like. So unsaturated fats will have a carbon double bond in them. Butter, saturated fats, animal origin, real butter would have all single bonds in them. And the unsaturated trans fats would have basically a double bond. But what happens is you have a chain coming on one side and on the other. So these are really bad. These are not natural. So typically your saturated fats, they tend to contribute to atherosclerosis, which is basically hardening of the arteries. And it increases that. So that's bad. And trans fats actually are worse. So basically they contribute more to heart disease. Than the saturateds. So they're really bad. And so trans fats are basically man-made, so they're preservatives. And so that's something you want to watch in terms of your dietary. So all labels are required to report trans fats in their products. So they have to. They don't have a choice. So when you take a look at dietary fat, it's always based on a 2,000 calorie diet. The problem is you have to be careful because if you're not eating 2,000 calories, then all of your numbers have to be shifted. If you're eating fewer calories, then each thing you eat has a bigger bite to your overall health. If you're eating more than 1,000 calories, it has a smaller bite to it. So ultimately, if you eat a 2,000 calorie diet, this is basically what they say is roughly needed to maintain the integrity of the human body. Phospholipids, when you take a look at these guys, they're similar to a triglyceride in the sense that they have the triglyceride, that glycerol plus the three fatty acid heads. Only in this case, what they do is they replace one of those fatty acids with a phosphate group, and we'll take a look at this here in just a second. This phosphate group has a polar phosphate head, whereas the two tails are non-polar. And so ultimately, this is a huge component of plasma membranes. We're going to talk about this in future chapters. And this forms a lipid bilayer, which is essentially what the membrane is. And we're going to talk more about this in the future. But here's your phospholipid. So this is basically a polar head attached to a non-polar tail, which basically creates a lot of tension because the polars and the non-polars hate each other. The hydrophilics hate the hydrophobics and so forth. And so they automatically will form this lipid bilayer, which is basically what you see here. So this is your lipid bilayer. This is what your membrane is made out of. And so we'll take a closer look at that here in future chapters. But for now, let's kind of move on to steroids. So when we take a look at steroids, these are basically lipids that are made up of 4 carbon rings. So it's a 4-fused ring. This is classic of the steroids. And so this 4-fused ring is something that we see commonly. As a matter of fact, the major steroid that we have in our body is cholesterol. And cholesterol is our foundation steroid that builds all of our other steroids. So for instance, we need cholesterol in order to make our things like testosterone. It'll also make estrogen and our other steroids as well. So essentially, this is also important, not because it's the foundational molecule for the rest of our steroid hormones, but it's also a major component of our cell membranes. So it's really, really important. You have to have cholesterol in your diet. And that's kind of what it looks like. So any structure, regardless of what it is, if you see this 4-fused ring, this common base 4-fused ring, then you're dealing with a steroid. So like if you're getting a medication or something like that, and you ask the doctor, is this a steroid? And they don't know. Just get a look at the structure. If you see that 4-fused ring, it's a steroid. Okay. So now let's take a look at proteins. So basically, proteins are built on the monomer, the amino acid. And so ultimately, amino acids will combine together to basically form the protein, and then the protein has to fold up into a 3-dimensional structure. And that 3-dimensional structure is important for a protein. So what do proteins do? Well, first of all, they do support, right? For instance, a good example for us is our ligaments made out of collagen is supportive. That's a support structure for all of our skeletal system and our muscles. Keratin for our hair and nails, that's a support system. They also will drive chemical reactions. Those are enzymes. They'll do transport into and out of the cell. So these are transport molecules that will help things move into and out of the cell. Antibodies are proteins. They'll work in defense. Hormones, like insulin, for instance, are also proteins. Motion, contractile proteins, things of that nature. Muscles, for instance. So basically, these are all made out of protein. Myosin is a protein. Actin is a protein. So all these things are proteins. So pretty much if there's a job in the body that needs to be done, it's a protein that's doing it. So how do you build the protein? So basically, you want to start off with the amino acid. The amino acid basically is the subunit. It's the building block of the protein, and it has 3 parts to it. So it has the amino group, in the middle, it'll have an R group carbon or a central carbon. And there'll be 20 different versions of this R group. And then on the other side will be the carboxylic acid, the acid group. This is why it's called an amino acid. Now, what causes each amino acid to be different from each other is this R group. The R group is what sets it apart. And these are the different types of R groups. So you can see here's the R group for valine. Here's the R group for glutamic acid. This is for lysine. This one is for tryptophan. This one is for aspartic acid, cysteine, so forth. So you can see that the R groups will basically be the ones responsible for making these individual amino acids different, and they'll have different chemical personalities to them, which causes the different functionalities of the different proteins. Now, when we take a look at the peptides, they're going to be held together by a covalent bond with a special name, the peptide bond. So this is the bond that holds together 2 amino acids. A polypeptide is if you have 3 or more amino acids linked together, so a longer chain. This is what it looks like. Here's amino acid 1 with R1, and this is going to be with R2. So what's going to happen is you're going to go through a dehydration synthesis. You're going to cut these two. Those guys are going to go off as water. So there's your water over there. And then you're going to connect your carbon from the acid group of one to the amino nitrogen of the other. And that's what's going to create the peptide bond. And so now you have the first R group and the second R group. Now you have a dipeptide. So two peptides. Notice you just basically did the same exact chemistry that you did before when you were putting together your polysaccharides. Then what's going to happen is once you start to create your three-dimensional structure of proteins, then the three-dimensionality is really, really important for proteins because that's basically the basis of their functionality. So if you don't have that three-dimensionality, you don't have functionality. Destroying the three-dimensional shape of a protein, that three-dimensional is what's called denaturation. And there's a couple of ways you can do that. Either with extreme heat, like for instance, cooking an egg. So basically what's happening is you're denaturing the albumin, which is the egg white protein in the egg, or with pH. So if you've ever curdled milk with lemon juice, that's basically a pH situation. So you're basically denaturing or unraveling the protein itself. So all denaturation basically means is the unraveling of the 3D structure of the protein to the point where it's no longer functional. Okay. So now let's take a look at the levels of protein folding. That is to say, how it acquires its three-dimensional shape. First of all, there's primary structure. This is basically the linear order of amino acids. It's basically your amino acids as you're linking them in a row into what's called your polypeptide, your long chain of amino acids. Then what starts to happen is you get localized folding. This results in two different forms. What we mean by localized is basically the backbone of the polypeptide interacts with itself and starts to form two different shapes, either an alpha helix that's held together with hydrogen bonds, or a beta pleated sheet, which is basically also held together. It's like a little accordion, which is also held together with hydrogen bonds. So here's your primary structure. And here's your secondary structure. So here you can see basically the hydrogen bonds that are holding together these two pieces. So you can see the oxygen, which is slightly negative, to the slightly positive hydrogen there. So it's kind of that interaction. So here you can see also the hydrogen bond over here where your slightly negative oxygen is zippering up to the slightly positive hydrogen. And that's forming your alpha helix or your pleated sheet. Then we're going to move into tertiary, which is going to be this one. So this is basically where the R groups interact with each other to give you the 3D shape of the entire protein. And so you'll have ionic bonds, covalent bonds, hydrogen bonds. And then the last step is quaternary structure, where you have a combination of more than one polypeptide basically forms a complex. So for instance, in some proteins, they form a team. So for instance, in hemoglobin, you have a team of two subunits. You have an alpha globin and a beta globin subunit. So it's got four things in it. So it's a team of four subunits, each one of which is folded up in tertiary structure. But because it's a complex or a team, it forms tertiary or quaternary structure. This is what it looks like. So here's your tertiary structure. So you can see you have different alpha helix here versus sheet. There's your beta sheet in different sorts of loops wadded up. And then here's your different subunits that are basically made up into a complex. So that's quaternary structure. Okay, so let's go ahead and take a look then at nucleic acids. So nucleic acids are made of the monomers, which are nucleotides. And so nucleotides are composed of three different pieces: a phosphate, a 5-carbon. Okay, looks like PowerPoint's getting ready to crash on me again. Did. Okay. So we have a phosphate group, a 5-carbon sugar, and a nitrogenous base. And so these guys are informational molecules. This is what it looks like. So here's your phosphate group, your nitrogenous base, and this is your sugar. And so the two major nucleic acids we have are DNA, deoxyribonucleic acid. This is like your information. Pretty much anything associated with building you is in your DNA. And so it specifies also the order of amino acids for all the proteins you make. And then you have RNA, which is basically has many different functions, but it's basically a copy of the DNA in all cases. There are some things, different types of nucleic acids, coenzymes, or some are nucleic acids. ATP, which we'll talk about more a little bit down the road, is a type of nucleic acid as well. It's associated with energy and energy storage. It's like your rechargeable cell phone battery. So when you take a look at the differences between RNA and DNA, the first difference that you see is the sugar. DNA uses deoxyribose versus ribose for RNA. The bases that you see, those nitrogenous bases, come in 4. So DNA uses adenine, guanine, thymine, and cytosine, whereas RNA uses adenine, guanine, uracil, and cytosine. The strands are double-stranded in DNA, single-stranded in RNA. DNA is a helix. That means basically it's a little twisted rope ladder. RNA is not. So it's just basically a linear strand. Okay. So ultimately, we have a couple of different structural differences. Obviously, the backbone of DNA have alternating sugar phosphate backbones. We'll take a look at that here in just a second. And the bases project to the outside. We'll take a look at that. We identify our nucleotides by their base. So this is kind of what it looks like. So our DNA is double-stranded. This is just basically a little bit more of an expansion of the table we just saw into the double helix. In DNA, because it's double-stranded, it has what's called complementary base pairing. That is to say that whenever you have an adenine, it forms 2 hydrogen bonds with every thymine. And whenever you see a cytosine, it forms 3 double bonds, or 3 hydrogen bonds, rather, with every guanine. And so that's kind of how you zipper these two pieces together. So that's kind of what it looks like. So here's your alternating backbone. Here's phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, with your nitrogenous bases sticking out the side. And then complementation, basically the 2 strands, is what will zipper up the 2 strands of the DNA, using your AT pairing with 2 hydrogen bonds versus your CG pairing with 3 hydrogen bonds. Now, ATP is an energy carrier, right? So basically what happens is when you take a look at ATP, it's basically like the rechargeable battery. If you need energy, you need ATP. So here's what it looks like. So you have adenosine, which is the nucleotide, with 3 phosphates on it. So if you put that on there, this is ATP. Then what's going to happen is you're going to hydrolyze the ATP. You're going to take off one of those phosphates. And when you do, you have ADP plus phosphate, and this is the piece that you get energy. So this is the piece that you really want. That's basically allows you to do cell work, whatever that happens to be. Then to recharge your battery, you have to basically add that phosphate back on to make ATP. And so that's the subject of the energetics chapter, cell respiration. That's basically what that is. And we'll take a closer look at that later on. So here is your check your progress. And then that brings us to the conclusion of chapter 2. I apologize for all the PowerPoint crashes, but I will see you when we do chapter 3.